There's that test launch planned for February. We can already call it around the world flight, can't we? It is my dream, in fact, that the stratostat, designed, manufactured, and launched by us, for it to make several turns around the Earth. I think it's quite possible in February, given both the weather and the results we've been able to achieve during the factory test launches. So, I think yes. And then we can actually move on the conversation further. Okay, we have developed the welding, the shell was launched, then the round the world flight. What next? Where are we going? Can you declare the plans? It's clear that in August we talked about stratospheric airships being generally feasible, and we're going there, and that's all true. But stratospheric airships are still something so complex and long term, something that you have to go to in small steps. And one of the ways is to increase the volume, because there are theoretical, so to speak, limits below which stratospheric airship is impossible, and the creation of shells of such volumes is one of the ways of development. This is one of the main tasks on this path. Now our shells have a volume of 2,000 cubic meters, and the technological capacities that we have mastered in recent months and what we have obtained, that allows us to make shells of units of thousands of cubic meters. It is already possible, it is already realizable and feasible, and the near-term prospect for us is 10,000 cubic meters. So a shell of 2,000 cubes allows us to lift about 20 kilograms of payload. A shell of 10,000 cubes, well, it will allow us to lift 100 kilograms of payload, which is already quite comparable to the masses of a base station, for example, a cell tower, which will allow direct communication with the user's cell phone. The next apparatus in the lineup is a 250 kilogram one. The payload is 250 kilogram. And then we go towards a ton of load capacity. It's about 100,000 cubes. 100,000 cubes, and this is the boundary at which we assume it will already be possible to move to propulsion. That is, the payload will be enough to install thrusters, to install energy carriers of sufficient capacity, solar panels as well, and to realize the energy cycle in the stratosphere, to start moving there. 100,000 cubes, yes, well, it's too serious a shell, on the one hand, it seems. On the other hand, 10,000 cubic meters seems like a lot as well. Now, here we are doing 2,000, it's already big. How much will we develop? 10,000 cubic meters. We'll develop it this year. That's the plan, right? Well, we're talking about several technological steps. Now, for 2,000 cubic meters and even for 10,000 cubic meters, well, the film itself can withstand that. If we go further, we already talk about films, about tapes, that will take the load inside the seam and transfer it further to the payload, to the ballast film. So these are slightly different films. These are films that already have a power layer, such as polyamide and so on. Of course, it's a lot of systems that support valve triggering, which can release gas from different parts of the shell, according to a certain algorithm. It's a system for changing the altitude of the vehicle during the flight. Now we fill the ballast shell with a dose of gas on the ground and calculate echelons. And we need to be able to control the apparatus from one altitude to another altitude. And the ballasting system will allow us that. That is the system of pumping and releasing gas from the ballast shell. And of course, when moving to larger volumes, we need to reduce the specific mass of the ballast shell. Because as the radius increases, the load per linear meter of ballast shell fabric inevitably increases. And we need not to increase the mass of the ballast shell, but at least keep it within the same limits in relation to its volume. This is one of the main challenges in the transition. Yes, I'm thinking about it now. It'll be over some point. You'll have two ballast shells, three, four. You can't keep increasing its size indefinitely. Of course, we can't increase the diameter indefinitely. Or I'd have to reduce my appetite for excess buoyancy because I'm essentially compensating for it. I have 1 kilogram of excess buoyancy, so I need a ballast shell to compensate for it. If I have 200 kilograms, right, or accelerating shell to add just to make it float faster. Yes, indeed. In the first launches, actually, well, the one which happened in 2023, it was exactly like that. We had an excess lift of only 800 grams that we needed to compensate for. And in order for us to go to altitude, not for a few hours, not 5, not 6 hours, we put a launch shell. Otherwise, they just wouldn't open the sky for us to take off. The regular lattice shell is also filled with helium in the launch that you saw first. Actually, we tried to make the first one live. This lattice shell pulls the main vehicle to the desired altitude, just accelerating it. And then at some calculated altitude it bursts, and the long drifting vehicle stops accelerating. Maybe it floats up a little more, it is completely fulfilled, and then at a given altitude, its work continues. That's the kind of technology we have. 10,000 cubic meters. Well, the payload is 100 kilograms, together with a maneuvering ballast shell for the year 2025. Yes, that's our goal. That's our goal, and it's a very ambitious goal. Because even about the 2,000 kilogram shell, well, it's the first large, fully domestic one for long range maneuvering one, and here is 10. That's ambitious. What was Google's? The Japanese had the biggest shell, right? Well, they make shells in the Soviet Union in several 100,000 cubes. As far as I know, it's 200,000 cubes. That's the USSR balloon, and there was also the Osava Kim balloon. They were actually pulling tons. There were people there was a capsule for those people. This is already quite a serious apparatus, and many altitude records were set on those apparatus. Records for that time. There were also some unfortunate events associated with those apparatus where people ended up in that capsule. That's 1934, right? When they first started, they were different. Well, those shells, they would rupture at launch. So a column of gas is like a column of liquid that creates pressure. If, for example, when you fill the shell, there was this gas bubble at the bottom, and then the shell stuck together, so it fills, it keeps feeding, and then at a certain point, it comes out further, and the shell just bursts from that impact. So there are a lot of nuances here. When we tested the shell in the airship shed, we filled it with air, you could feel how many different vibrational processes there were in the shell. When you try to lift it by the suspension cable, there are almost 2.5 tons of air in it at that moment. That's a lot of inertia, and it's got these vibrations going on. It comes down after about 10 or 20 minutes. You can feel it in the tension of the cable. And in the process of takeoff, we have a changing volume of the apparatus, its shape. The shape of the drop is different at different altitudes. The density changes, there are turbulent flows, and to calculate all this aerodynamics is also a certain task to fulfill. There are many nuances. They arise as soon as we talk about such launches, and the larger the volume, the more of such nuances we have. Because as the volume increases, once we go from 2,000 cubic meters even to 10,000, we can no longer hold that vehicle with our hands. We need certain ground support, ground equipment, pulleys that would hold this. They have to provide the weighing as well. We can't put this apparatus on an ordinary floor scale. We need tensils to suspend the pulley. So there are a lot of nuances. And if we go to even larger volumes, we will not be able to provide weighing. Well, as a rule, we cannot. We can't assure precise weighing because this apparatus will not fit in the airship. shared as we do on test launches. So the separators will be somewhere in the field and we'll either have to look for the perfect calm, which will never be there, or we'll have to trust certain gas dosing systems inside the shell, which should be accurate enough to meet our objectives. Or make gas release systems and launch with a reserve. Like we'll launch a few dozen extra cubes in there and then we release it at altitude. We release it at an altitude. It's a very curious task. Once the apparatus gets bigger, there are many nuances. Well, this is engineering job, right? But it has to work at minus 60 degrees somewhere there on the shell, on some batteries. The most important thing is that it has to be done by some experienced team with a proven track record. Because they say, and you said it yourself, in the Soviet Union, 200,000 cubic meters of shells were made, and it would seem like just take it and do it. But there are no people, there is no experience. And, to do all that work to create a team, and then this team needs to build up competence in this matter, that is the most valuable part. The most valuable thing is that because the engineering issue is actually solvable. Cars could drive 100 years ago, airships flew as well. But to master all of this, to put it on rails, well, it is the most interesting task. The ISS is in space, and even without helium,